The 20th? Yep. Zzz. Thanksgiving is a week from today. Hey, what kind of music did the Pilgrims like to listen to? Plymouth Rock? So the goal here now is to figure out where things, what we call in math, coincide. So when two lines exist in the same plane, if they cross, that one point is a point that has to be on both of the lines. So we say that the lines coincide at that point. So that's what we're going to spend the next couple of weeks looking for is a point either on a flat surface where two lines cross, or more commonly for us now, um, a point maybe in space where three flat surfaces cross each other. But for today, we're just going to talk about lines. So you'll remember that if you graph a line, it might look like this. And if you graph another line, it might look like this. And one possibility with those lines is that they cross, right? And so this point where they cross is what we come to know as the solution, right? So that's what we're going to hunt for just today. I mean, when it's lines, just today. And what are the other two possibilities when you put two lines on the same graph? They don't cross. And what does that mean they have to be? Right, you guys know that word. So you can also graph a line like this and then realize that, oh my gosh, I just graphed another line and it looks like this. And two lines like that will not intersect are parallel lines. And so in a case like this, since they never coincide, then we would say that a system like this has no solution. Okay, that's an inconsistent system. What's the third possibility? They do, which I know sometimes people think like, why would I even consider this an option? It's a very realistic option. And it's really going to be more like prevalent and like interesting when we get to the three variables, because I mean, lines, it's a little bit odd. Like you graph one line like this, and you're like, hey, look, I graphed a line. And then someone says, hey, go graph this other line. And then you graph another line and you realize, hey, it looks like this. And it does happen. Equations don't have to look the same to represent the same set of points. And so in a case like this, how many places do those lines coincide? Infinitely. We want to be careful not to say all real numbers because that's not true. And as a younger teacher, I don't think I did a good job of explaining to people that it's not all numbers that work, right? There's infinitely many points out here on the paper that are not on the lines, right? So we don't want to say all real numbers. We want to be very careful to say that there are infinitely many solutions. We're today not really going to talk about these ones. I just want you to be aware of the existence, remember those, because it is going to come back up. But today's lesson is just going to focus on the first situation, just those two lines that cross. Except we're not going to graph them. We're not going to talk about them as lines. We're just going to do the algebra. Those of us that like just grinding around with X's and Y's and, moving things around, this will be your thing. And you'll remember this pretty quickly. So that's what we're after today is we're going to be on the hunt for that red dot that is the point where two lines cross. So we're not going to talk about graphing anymore. We're not going to talk about substitution method. If you remember the substitution method, it was the one where I made you draw the little red box, and then you pick up the red box and you substitute it into another equation. We can go over it at some point if you want, but it doesn't help us. It's really hard to do 3x3 systems with substitution. So that's why we're going to focus today on just elimination. So I thought I'd start us out with a level one, and then we'll do a level two, and then we'll do a level three. And if you want more, I could conjure some more up, but I figured after three, you'd be like, yeah, I remember this. So our first system is this. So you will recall that any equation like this is called a linear equation. And the reason we call them linear is because if we graph them, they would make a straight line. So if I were to graph those two lines, um, my job here is to say where do they cross? So does anyone remember the elimination method? So in math, it's a fact that if you have equations working in a system together, if they're part of the same like situation, you can actually add the equations together to get a third equation that is also a member of the system. And so the magic of it is this, that we're going to take and we're going to look at these two equations and we're going to ask ourselves, would anything significant happen if we added straight down? If I added my like terms, if I added equation one together with equation two, would anything worth mentioning happen? They would be eliminated. Right. And so the reason I call this a level one problem is because it's already just ready for me. Back in algebra, I may have called this a fluffer puffer. I doubt you would remember me saying. So the fluffer puffers are the ones that are just a joke. Like if someone is kind enough to just throw this down on your plate, you're like, oh, okay, thanks. All you have to do with a system like this is super easy, is just draw your line. This is your line of intent. And anytime we put a line under two things, it generally means, hey, we're about to add some stuff together, right? We put a line between things, that means we're going to divide them. And so if I add the like terms just straight down the hill, my x's are eliminated. There's that word. How many y's do you get? You get four of those. And then what's your constant term on the right? Perfect. Right. And what pops out inevitably is an equation that is more appropriate for like a sixth or a seventh grade class, right? So the work is done. Now we just need to make sure we don't do anything stupid. If we divide both sides of this equation, this little baby purple equation by four, we figure out that y is equal to negative 10. What that means for us is that where those lines cross will be at a point whose y coordinate is negative 10. So the question now is, how do I find the other coordinate? Because a point isn't a point if you only know half of it. Oh, I'm sorry, I'm going to make a joke. That would be pointless. Did you? Morgan just gets us moving. Bless your heart. Yes. So what we do now is we put it back into any equation that has both variables. You can use the top equation or you can use the bottom equation. With substitution, you might remember that there was a little bit more, we had a little more stringent sort of rule about where you could or could not put it. With elimination, the deal is this. You find any equation on the board that has both variables in the problem, it's open game. So I would think that about half of people would choose the top one, and their reasoning would be because there's no negatives on the left. And about half of people would choose the bottom one, and they'd say, well, because the numbers on the left are smaller. It doesn't matter. That's the fun. As long as neither of us makes a mistake, I could do it one way, you could do it the other way. We're going to come out the same. That's the essence of this, is that they're not going to produce different results unless we do something crazy. Which one do you guys like? Do you care? Top's fine with me. Yeah, top's great. Let's go top. So what that means is I'm going to take the number negative 10, since that's my half answer, and I'm going to put it right in place of the correct variable, which is right there. And so I write that equation over again now, but I change y into negative 10. So what that top equation is going to look like, it's going to say 2x minus 30 equals negative 14. All right. At this level, I shouldn't have to show you that I'm doing 3 times negative 10. I feel like I can just do that. And then again, it's just math, right? Algebra just is what it is. Like solving an equation is just, it never changes. What do we do next? Add 30 to both sides. And we get 16 in the right. Divide by 2, and what is x? And that is your solution to the system. It means that that is the only set of numbers that at the same time, it's like magic. If you put 8 and negative 10 in place of x and y, they would solve the top equation and they would also solve the bottom equation. That's pretty significant, right? Okay. So what happens when we bust up to a level 2? What changes when we leave the happy land of fluffer puffers? Say again, bud. Right. Could you be a little more specific? Here, let me write this down and perhaps it will jog your memory. So now that you see it, what's different? Nailed it. So if I try to just add down like I did on that fluffer puffer, nothing's going to happen. I mean, I could get a third equation, but it's y. If I add down, I get 24x minus 3y equals negative 3. Like I don't want another one of those. So the idea here is that I want to make it look like example 1. I have to do a little bit of work to get it to be eliminatable, right? So what's the path of least resistance here? Which variable seems to call to us that says I'm the easiest one to kill? The 8 and 16 by now in your life should stand out to you. Every one of us would recognize that 8 is exactly half of 16. So then we think to ourselves, boy, if only that 8 right there could be a negative 16, then I'd be ready. I'd have a fluffer puffer. So rather than sit around and talk about how nice it would be, we just take the initiative and we multiply this equation by whatever we need to, right? You've known this for years that with equations, as long as you treat everybody in the equation fairly, you can do whatever you want. You can add stuff, you can distribute, multiply stuff, you can divide stuff, whatever. So if I take that top equation and I multiply through by negative 2, I get a new equation that says negative 16x minus 4y equals negative 52. And then it's good practice to take, this will be really good practice. So I'm trying to set a good example here. If I were just doing this on my own for the record, like at home or whatever, I would have put this equation right here. But I'm not going to because that's going to hurt us with 3x3s. So the good practice here is, even though it's annoying, is just to rewrite the whole system. That's going to help you a lot on Monday. So I'm going to take that bottom equation and I'm not going to modify it, but I am going to copy it over so that now what I have is a fluffer puffer. And I made it myself. I had to make it. It wasn't ready for me. And then I put my line of intent underneath there. I'm ready to rock and roll. So let's add straight down the line. If we add straight down the X column, what do we get? We get elimination, right? We get 0. And you don't want to put anything there. Even though it does equal 0, you definitely don't want to put anything. You want it gone, out of sight. Add straight down the Y column, what do you get? You get negative 9 of those guys. And then add straight down the constant column, what do you get? If you owe me $52 and borrow 29 more, how much do you owe me? 81. So it's negative 81. All right. I'm going to keep these nice and pleasant. I'm not going to burden you with fractions and all that kind of stuff. Okay. So the answers should be coming out nice. I don't want I don't want today to be about, plugging negative 3/7 and stuff like that back in. I just want these just pretty and clean. Today's about the process. And if we divide both sides of this little baby equation by negative 9, what's y? Positive 9. which means that our answer looks like, here I'll use green, I guess. I haven't used any green. Our answer, I'll write it down here in the corner, looks like this. There's the green is my answer. It's just missing half of itself. And how am I going to find that again? Plug it back in. You can go with any of the three equations on the board. I did not say four on purpose because there are not four equations. There are three. One of them is a copycat. So I think most normal people, I never mean offense by that, but a normal person would seek out the path of least resistance and probably go to the top original, just because the numbers are generally going to be smaller. But if you're feeling like I got this, it's just for fun, just go try another one. It's okay. You're going to get the same thing as me if neither one of us messes up. So that top equation now says 8x plus what? 18. And then we subtract 18 from both sides and we get 8x equals 8. And we divide both sides by 8 and x equals, and we're done. That means that we can now complete the puzzle. If we know that the x half is 1, stick it right down there in the corner, and that's where the lines cross. So now that I've jogged your memory, what do you think a level 3 is? Good memory. Yes, we're going to have to multiply both. So a level 3 problem, and you'll spot these, is one where you can't just do one multiplication like we did on a level 2. You've got to do multiple multiplications. Sometimes people get really creative with this and they start dividing things. And I feel like by the time we get around to being all clever and cute with it, while I appreciate the gesture, it's like at the end of the day, really, I mean, if it were obvious, then I'd say go ahead. But like if you're going to have to get crafty and divide this one and multiply this one by 1.5, like at the end of the day, you're just going to drive yourself nuts. You have to seek out here what numbers you're more comfortable with. Um, which variable is easier for us to eliminate. I think that the Y's are more friendly because we know since we've all passed basic like grade school that the numbers that we want these the two that I'm circling, what could I make them both into? I could, but 12 would be better. 24 would work, 36 would work, 48 would work, 60 would work. I mean, you name it. Anything that they'll both go into is fine. But at the end of the day, I want them to be as small as they can be, but they have to be the same. And so if I think, hey, I'm going to make both of you guys into 12s. So I'm going to take and now have to multiply the top equation by one thing and the bottom equation by something else. They're separate equations. They're part of the same system, but they're not, you can treat them differently. What do we multiply the top one by? 2. And what's nice about this particular level 3 is that I don't have to modify the signs. If that 4 in the red circle below had been a plus, then I'd have to change it to a minus, right? To get them to offset. But they're already plus minus. Like this is super easy. What do I multiply the bottom by? Just 3. And by multiplying by a 2 and a 3, those two numbers in the red circles will become a 12 and a minus 12. And that's what we're going to do. This is just Operation Fluffer Puffer creation. That's all we're trying to do is make them eliminatable. So my new top equation is going to be negative 20 of those plus 12 of those equals negative 40. And then my bottom is going to be 27 of those minus 12 of those equals 33. And then you draw your line of intent. The line is our way of saying we're going in. All right. So this time we've elected to eliminate the Y's. It doesn't matter which one you eliminate first. Sometimes the path is chosen sort of for you. Sometimes you just pick one. So if we add straight downwards, obviously the Y's will eliminate. How many X's do we get? We get 7 of those X's. We eliminate the Y's because we made them opposites. And again, it's just so often about so much of algebra is just basic math. What's negative 40 plus 33? Negative 7, right? Just addition. And then if you divide both sides by 7, what's x? -1. So it's at this point that I like to say, here is my answer. I like to write it down, take the initiative, and say, there it is. And I'm going to put -1 in, but since it's the x, I'm going to put it right there. So there are now 4 unique equations on the board. I would always say that I would question someone's sanity if they elect to use either of the ones over here. Like, why would you do that to yourself? So I would not recommend using these because we know the numbers are going to be bigger. So of the two OG equations, which one do you, I think I know what you're going to say. Which one do we like better? Probably the bottom. Just nicer numbers all around. So we're going to take the -1 and we're going to put it right there because it's an x. So what's my bottom equation going to say? -9, because that's 9 times -1, minus 4y equals 11. And then it's just math from here, right? Add 9, you get -4y equals +20. Divide both sides by -4, and you get y equals -5. And then you take that other half of the answer and you drop it into the little house over here that you made, and you're done. So those are the 3 levels of elimination. And you'll see the same thing with 3x3 systems. Some of them are easier. When we start eliminating 3 variables, sometimes you'll look at one entire column and go, oh, it's got like a 4z, a 4z, and a -4z. And that's going to be like, yes, baby. Like those become like our 3x3 fluffer puffers, right? Do you have any questions? All right, I'm going to hand this bad boy out. Let's get her done. You have 13 minutes of class left. And then another, what is that? What's 4 times 24? 96. So you'll have 95 more hours after class today to get these problems done. Nothing to it, right? Before Monday. Oh, yeah. You know what? Today we have a later schedule. Let me pause this real quick while I look at this. Thank you. It's 4 minutes longer. I forgot. I made the schedule and I forgot.